Okay guys, so this is the class 4 for the robotics, introduction to robotics at San Diego State University. And so we're continuing our the rotation metrics topic. Okay, so hold on, I fix this first. Okay guys, so we derived that orthogonal rotation metrics, and now we are expanding that to 3D orientation or rotation. Okay, so suppose you have this coordinate system or frame, and here is the O naught, X naught, and the Y naught, and the Z naught in space, obviously. Then I'm trying to rotate around the Z naught axis, so your new frame gonna be has the same direction of that the Z naught, so it's Z1, and I'm rotating to the angle of what? Theta. So you're gonna have this, that's right. You're gonna have this, so this is you're gonna be X1 frame and O1 obviously, and the Y1, and the angle that I'm rotating, as I said, is theta. That's right. So this angle also gonna be theta from this trivial trigonometry. That's right. So now if I want to find the rotation metrics of frame 1 with respect to frame 0, as we know, as I taught you several times, it's going to be x1 inner product of x0, directional cosines, that's right, x1 y0 and x1 z0, that's right. So y1 x0, y1 y0, and the y1 inner product of z0, that's right. Oops. Right, and finally z1 inner product of directional cosines x0, z1 y0, and the z1 what? z0, obviously. That's right, and we named it as directional cosines, right? So, and now you know it because in the 2D we did that. So if you look at this for this 3D orientation or rotation, right? So it's gonna be projection of this on this, x1 on x0 gonna be what? Based on the directional cosine, it's gonna be cosine theta. That's right. And now if you want to find the projection on the y0, it's gonna be here, gonna be 90 degree again. That's right. It's gonna be what? Sine of that. So sine of theta. As we are rotating around the z0 axis, so it's gonna be planar rotation. So again, angle. So it's gonna be, because this is on the plane. That's right. So in its projection on the z0 gonna be 0, obviously. The same is valid for here. So you have to find like this, right? So, and here is 90, and here is 90 degrees, right? So it's directional cosine of y1 over x0 is what? Sine of theta. But sine in what? In this direction, that's right. So it's minus sine of theta. It's gonna be cosine of theta, obviously, and again this. But the z1 directional cosine is normal to x0 and y0, so it's gonna be 0, has no projection on x and y, and but it is aligned exactly at the same direction of the z0. So it's gonna be how much? 1, obviously. So checking that orthogonal property that I explained in the previous class, if I name this column of rotation metrics, 3D rotation metrics, as A, right, and these as B, and these as C, we simply see that absolute value or magnitude of these vectors obviously is 1. That's right. A and B gonna be, look at here, magnitude of the A is equal to the magnitude of the B, which is how much? Cosine square plus sine square, which is 1. And magnitude of the C is 1, obviously, right? And A in B, that's right, is equal to A in C is equal to B in C. All of them, they are how much? 0. Means the columns of this rotation matrix, they are normal together, right? From inner product, I said that. So this is another property we have to check. That's right, check. Okay, and the determinant of this 3D rotation matrix obviously is, let us do it together, gonna be cosine of theta. In determinant of cosine theta, 0, 0 cofactor, remember this, plus sine of the theta. In sine of theta, 0, 0, 1, and this is 0. These are not. So obviously this is cosine of theta square plus sine of square theta, which is 1. So bingo, as we said in the orthogonal property. So R1, frame 1 with respect to frame 0 is an orthogonal matrix. By the way, you can examine the other property, that is RT is equal to R transpose is equal to R inverse. Obviously this, just examine that one. Understand? So we rotated the frame around the z-axis and angle of theta. So it is better way that we write the rotation matrix. Okay, how to do that? We're gonna say in this case, okay, come on. In this case, we're gonna say rotation around the z-axis and the angle of theta. This is a very compact version of whatever you have done. This is rotation matrix that we did it around the axis z and the angle of theta. Understand? So it is very much better that you do this. For example, if I say R of z and 0, that's right. So what can happen, guys? Look at here. There's no rotation. So your new frame gonna be exactly at the old frame. Your frame 1 gonna be exactly frame 0. So you're gonna have I then TT identity matrix or unit matrix, because it's very obvious, guys, right? Right? Obviously it's like this. Okay, then we are showing in algebra with I. That's right, identity matrix. So so based on this formulation, you can now say rotation matrix around z or the theta multiplied by rotation z and the phi. You have 2 times. One of them is this, guys, and another is this. Suppose I'm showing here. So this is theta, and another I'm rotating. Oh, let me choose another color. I'm rotating like this, guys. Okay, so this is gonna be x2 and y2. That's right, and another rotation phi. That's right. So if you want to find, so first rotation around z, theta and phi, so the result gonna be rotation matrix of, simply you can add them, theta plus phi. That's right. This is very clear. Right? If I say now rotation matrix of, if we find x and theta, means this is our the world coordinate system, or frame number 0. See, x naught, y naught, and the z naught. That's right. So I'm saying this time I'm rotating around the axis x theta, so I'm gonna be around rotation around this. So your new coordinate system gonna be what? Gonna be this x and z, they are rotating this time. That's right. This gonna be y1, and this gonna be z1. How much? Oh my god. Gonna be this. Here is theta, so here gonna be also theta. Right? So if I want to that you drive it for me, don't forward. I give you 2 or 3 minutes and you try it. Okay? And then I will do that. As you're doing, I'm double checking. Okay, it's recording. Okay, can you drive it? The rotation around the axis of x for the amount of theta. Okay, so about the x, because x is not changing, so you're gonna have x along with that x naught, so you're gonna have 1 0 0, obviously. That's right. What about the y? Y, you have to find the projection on this. That's right. Gonna be cosine of theta, gonna be sine of theta. That's right. Oh, sorry. Y1 on the x is 0, so this is cosine of theta and sine of theta. That's right, because this is y is normal to x, so has no projection. Understand? That's it. So, and the z gonna be, again, you have to find z gonna be, again, because z is perpendicular to or normal to x naught, gonna be 0 again, and here you're gonna have on the y gonna be minus sine of theta, and over z gonna be how much? Cosine of theta. So you did it. That's right. Clear, guys? Right. So, and now if I ask you find the rotation matrix of theta and y, that's right. So this time we are rotating around the y-axis. That's right. We are rotating for the y-axis and theta. So if that happens in the xz, they are changing like this. Say it is x1 and z1. That's right. But the angle of theta this time is right. So x is changing, so you have to find its respect to this. Gonna be cosine of theta, obviously, and respect to y, because x1 is normal to y naught is 0, and respect to z gonna be what? A sine of theta, right? And the y obviously is not changing the direction, right? Oh, this is oh guys, I made a mistake here. I'm saying when the theta, you have to respect to the right hand rule, guys, okay, in this direction. So I have to delete this because you don't mistake. Okay, So this happens like this. This goes down, and this goes. This is your Z1. Huh? This is your X1. Understand? So if that's the case, again here is theta, and here is your theta, right? So gonna be this, and this gonna be minus only, because see, projection on this, projection on this. So this is the negative side of the z naught. That's right. Huh? And the y is the same, and z gonna be now sine of theta. See, projection on this and projection on this. That's right. Sine of theta and 0 and the cosine of theta. Bingo. Understand? So we found these rotation matrices around different axes. Okay. So after finding these, now let us go to the next topic, which is I'm naming as oops. Let me fix this because it's getting hot and it's gonna freeze. So I'm naming as rotational transformation. So what is that? Look at this graph. So you have the world coordinate system x0, o0, and the y0 in 3D space, and this is z0. And suppose you have another like this, another frame, z1, z1, x1, and y1, y1. And now you have this object on the space, right? This object on the space, and a point on that is known. On this your coordinate system, point P here. So what's the problem? So we know coordinate of point P with respect to O1, X1, Y1, and Z1, the Z1 frame. We know respect to this red frame, and we want to calculate P with respect to our world coordinate system, O0, X0, and Z0, or respect to reference coordinate system. Okay, we want to calculate respect to that. Let me fix this. Okay, so on the other hand, mathematically we know this. P respect to 1. Remember that I taught you in the previous class. Point P respect to the frame 1. I know it. I know this vector. U x1 in direction x1 is known. This is value on the extraction. So I'd say, okay, and VY1, we know this, plus WZ1 transpose. That's right. We know this. On the other hand, we know this. Transpose means we know this U, V, W. We know this with respect to frame 1. That's right. So now we want to find P with respect to the frame 0. We want to find this. To find P naught, we need to find its projection, right, with respect to O naught, X naught, Y naught, and the Z naught. That's right. So P naught, you have to find this. You know that directional cosines is X naught, P inner product of Y naught, and P inner product of the Z naught. That's right. Directional cosines. Understand? So it is as I told you. So how to do that? It's enough because we know P. Look at here, guys. See, we know P. I'm exactly putting this here. Exactly putting here. So you're gonna have P naught gonna be, look at here, UX1 plus VY1 plus WZ1 directional cosine in X naught. Again, UX1 plus VY1 plus WZ1 directional cosine is inner product of this. UX1 plus VY1 plus WZ1 in Z naught. Right? So if you multiply them inside one by one, you're gonna have UX1 X naught, inner product X naught, plus VY1 in X naught, plus W in Z1 in X naught. Same here. UX1 in Y naught plus VY1 in Y naught plus W Z1 in Z naught. That's right. Oh, sorry, Y naught. Y naught, and the last line, UX1 inner product of the Z naught plus VY1 inner product of Z naught plus WZ1 of Z naught. Yes, I can, obviously. Now look at these guys. Look at these. This, and this. Right? Obviously. So now I can decompose this as another vector and matrix. Here we go. UVW, UVW, UVW. So UVW. Right? And I'm just putting here X1, X naught, X1, Y naught, X1, Z naught, Y1, X naught, Y1, Y naught, and the Y1, Z naught, Z1, X naught, Z1, Y naught, and the Z1, Z naught. So what is this? You tell me, you know it. What is this? Yes, rotation matrix. Look at here, guys. Today I taught you in 3D space. Here we go. That's right. Rotation matrix of frame 1 respect to frame 0. So we got that. We got the result. If you know point P in space with respect to a frame by having its rotation with respect to the reference coordinate frame, you can calculate with respect to this. And this is very important, guys. super important. This it is. For simplicity, see, I'm just making shortcut. This one with this one goes, and the remaining is not. It doesn't go. I'm just showing to you this, right? Understand? Huh? And obviously this is R1 respect to not or 0, and this is your P respect to 1. Right here, P respect to 1, and this is R1. So we write very important mathematical statement for rotational transformation. Understand? Huh? Hold on, I have to fix this. Okay, so now let me have an example. Okay, example of what we did. Okay, so example. Suppose we know this vector into one, this, I name it V0, means a point in space. You get here, guys? I know this point, x0, y0, and the z0. Suppose this is 2, its x is 2, 1, 2. Its z is this, its y is this, and z is 1. So this is the point I know. So right, this is the point. So when I say this vector, it means position of that, this is, I know this. Okay. Now I'm saying find v1, okay, when means the new coordinate of this point P. Okay, when you have this, when you have r of y and pi over 2, when you have this rotation. Okay, so I'm gonna, so please focus on this and do it. Don't forward it because you're learning. Okay, see if you can find this in 3 or 4 minutes. Don't forward the video, you're learning. See if you can find it. I hope that you are trying at home. So I'm gonna do it. So when I say this, because I taught you today, means that you have a rotation, here we go, around y-axis and the pi over 2, right? So this z comes down, this gonna be your new z, that's right, it's gonna be z1, and this gonna be your new x, so x1, right? Understand? So, but this also is rotating, that's right? So we're gonna find it. So first of all, you have to find this transformation matrix. So x, now it's x because here's pi over 2, right? Has no projection on x0, so it's gonna be 0. x1 again is normal to y0, that's right? Here is also is. This is normal to this plane, it's gonna be 0. But x0 is exactly in the opposite direction of the z0. You see that? It's gonna be -1. Here we go. That's right. Now y. So your y1, you because you're rotating around that. Y1 with respect to x0 is going to be how much? Obviously 0, because this y1 is normal to the plane of x0 and z0. That's right. Y1 with respect to x1 is 0. Oh, sorry, I started from here. X1 is 0, and yeah, x1 is 0. And with respect to y0, because they are aligned together and parallel, it's going to be 1. And z0 is obviously is 0. And now z1. z1 with respect to x0, because they are parallel and aligned, so it's going to be 1. Obviously. Sorry, because they are on each other. z1 with respect to y0, obviously going to be 0, because it's normal to the plane of x0 and z0. And z0 with respect to z1 with respect to z0, again, is going to be 0. So you found this. And I thought you v0 going to be r1 with respect to 0 and v0. That's right. So you have to do this. 0, 0, 1, 0, 1, 0, minus 1, 0, 0, and in your point, this is your P point, this point P. So gonna be how much? Gonna be 2, 0, and 1. If you do the calculations, you get this, guys. 1, 0, minus 2. Okay. 0, 0, 1, 0, 0, 0, minus 2, 0, 0, which says that if you do such a rotation, your new point or new vector that you are making from that point comes to 1, right? Comes to 1, minus 2, and 0. You have these points, P1. Right? Understand? If you do that, you're gonna get this. I'm sorry, I'm being stupid. So you're gonna have this one. No, you're gonna get the same point. Okay? So you got that? You got this is your new point. So now this is one rotation that we did. How about combination of rotations? So again, this is your y0, x0, and this is your z0, x0, y0, and z0. Understand? And you are having two rotations. One of them is this, guys. One of them is this rotation. That happens. X1, Y1, and the Z1, and you have another rotation. You have this rotation. I don't know. This, and this. Oh, we have a bird here that's very happy with the robotic course I'm teaching to you guys. See, it's singing for you. So X2 and the Y2 and Z2. But we know a point here P known its coordinate with respect to the Z2. So P2 is known. Okay? See that? What we want to find, we want to find the position with respect to the and this is let me, what the hell is this, guys? There's not this in that. Respect to, this is known. We want to find respect to reference coordinate system. We want to find this, okay? But we know that because we know that P with respect to the 1 gonna be, from whatever I taught you, gonna be R rotation of frame 2 with respect to the 1 in P2, because this is known, that's right? And now P naught gonna be R1 respect to 0, and now P1, because we calculated this from here, and we know this, and we can find this. Understand? So, on the other hand, P with respect to the reference coordinate, okay, now P naught from here gonna be rotation of frame 1 with respect to not P1, but we have P1 from here, that's right, from here. So it's gonna be R1 respect to 0, and now R2 respect to 1, and the P2. Bingo, that's right. I say it, bingo, that's right. Again, for simplicity, you can say this with this goes to New York, this with this goes to New York, and you get the P naught. But we are not doing that, for just that you understand, that's right. It's a backward transition to the reference coordinate system. We know this, we are rotating to the 1, from 1 we are rotating to frame 0. Understand? So the take-home message is this: if we have n rotations, so P naught gonna be R1 respect to 0, R2 respect to 1, R3 respect to 2, R4 respect to 3, to R1 respect to n minus 1, P, that we know the coordinate of point with respect to the frame n, and you can find this coordinate of that point with respect to reference coordinate system. Understand? Example, our backs in the lab, that's right. Our backs in the lab. How? Just look at here, guys. If you look at again the backs in my lab website, you go to Peimann, okay, and if I make it bigger a little for you, guys, I'll stop it for you. See, if I know the point with respect to the coordinate system attached to the end effector, and I know the transformation matrix between this and this joint, this and this joint, this and this joint, this to this, and this to this, to the frame, which is body of the Baxter, I can use the formula I just developed, and I'll find the position of the P in space with respect to the body. And what's the application? I will teach you the options. Okay? Now let me close it, guys. Okay, understand? So, and I'm gonna have an example for you by the next class. Thank you.